Friends, welcome to the tutorial series on network analysis made simple. During the previous tutorial on step response of RL and RC circuits, we learned regarding the behavior of inductance and capacitance at t is equal to 0 and at t is equal to infinity. We also developed the procedure to solve for the system response using classical approach. We also solved few circuits to emphasize the concepts we learned. In that tutorial, one thing we observed that if the circuit contains one energy storing element, the system equation turns out to be the first order ODE and the solution will have one integration constant. During this tutorial titled Step Response of RLC Series Circuits, we shall develop a procedure to solve for complete solution for various parameters when the circuit is switched. In RLC circuits, you find that there are two energy storing elements. Hence, you will see that the system equation will result in second order ODE. The solution will contain two integration constants. We shall establish the procedure to obtain the two integration constants and solve for few examples. I am sure, friends, you will enjoy this tutorial also. Then, to obtain the step response of RLC series circuit, consider the circuit shown in figure. The switch K is closed at t is equal to 0. After the switch K is closed, the equation for the system response will be R into I plus L into di by dt plus 1 upon C into integration I dt is equal to V. Let it be equation 1. You find that this equation is an integro-differential equation. Hence, by differentiating and dividing throughout by L, we get d squared I by dt square plus R by L into di by dt plus 1 upon LC into I is equal to 0. You see that this equation is of the form as square plus bs plus c is equal to 0, which has the roots s1 comma s2 is equal to minus b plus or minus root of b squared minus 4ac divided by 2a. Using this mathematical identity, we can write for the roots s1 comma s2 is equal to minus r by 2l plus or minus square root of r by 2l square minus 1 by lc. Let alpha is equal to r by 2l, where alpha is called as the natural frequency in Nepers per second, and let omega naught is equal to 1 by root LC, where omega naught is called as resonant or undamped frequency in Hertz. Substituting for alpha and omega naught, we can obtain the roots as S1 is equal to minus alpha plus root of alpha square minus omega naught square, and S2 is equal to minus alpha minus root of alpha square minus omega naught square. We know that the nature of the response depends on the quantity under the radical sign root of alpha square minus omega naught square. We also know that depending on the type of roots, the system response could either be overdamped, underdamped, or critically damped. So, when alpha square is greater than omega naught square, the roots are real and distinct. The system response can be considered as the sum of two exponential components. So, the solution for I of t can be written as I of t is equal to a1 into e to the power of s1t plus a2 into e to the power of s2t, where a1 and a2 are integration constants. Friends, that is what I said, that there will be two integration constants you can see here. So, friends, to find a1 and a2, we need to find I of 0 and di by dt of 0. Consider the equation for I of t. If we substitute t is equal to 0, we get I of 0 plus is equal to a1 plus a2, and di by dt is equal to a1 into s1 into e to the power of s1t plus a2 into s2 into e to the power of s2t. If we substitute t is equal to 0, we get di by dt 0 plus is equal to a1 s1 plus a2 s2. We know S1 and S2, and after finding A1 and A2, if we substitute in the equation for I of t, we get the solution for I of t. We see that the response will be as shown in figure, and such a response is called as overdamped response. Friends, next we shall consider the case when alpha square is less than omega naught square. Consider the equation for roots s1 comma s2 is equal to minus r by 2l plus or minus square root of r by 2l square minus 1 by lc. Since alpha square is less than omega naught square, we see that the quantity under the radical sign will be negative. So, let us represent the roots as s1 comma s2 is equal to minus alpha plus or minus j into square root of omega naught square minus alpha square, where j is equal to root minus 1. Observe that when j is taken inside the radical sign, the quantity under the radical sign becomes alpha square minus omega naught square. This you can note. And let s1 comma s2 is equal to minus alpha plus or minus j into omega d, where omega d is equal to square root of omega naught square minus alpha square. This omega d is called as the damping frequency. In this case, the system response in terms of two sum of exponent components can be written as I of t is equal to b1 cos omega dt into e to the power of minus alpha t plus b2 sin omega dt into e to the power of minus alpha t. To find b1 and b2, we have to find I of 0 and di by dt 0. If we substitute t is equal to 0 in the equation of it, we get I of 0 is equal to b1. If we find di by dt of I of t and substitute t is equal to 0, we get di by dt 0 is equal to minus alpha b1 plus b2 into omega d. We know alpha and omega d, and after finding b1 and b2, we see that the system response will be oscillatory in nature as shown, and the oscillations will die down around the final value. This you have to remember. If we consider case 3, when alpha square is equal to omega naught square, the system response in terms of two exponent components can be written as I of t is equal to d1 into t into e to the power of minus alpha t plus d2 into e to the power of minus alpha t. If we substitute t is equal to 0, I of 0 is equal to d2. And if we find di by dt and substitute t is equal to 0, we get di by dt 0 is equal to d1 minus alpha d2. We know alpha, and after finding d1 and d2, the system response is found to be critically damped as shown. Friends, let me summarize what we have to remember to obtain the complete solution in case of RLC series circuit. The very first step is to obtain the equation for the system response in the standard form. Remember, the equation will turn out to be second order differential equation with constant coefficients. The next step is to find out alpha square and omega naught square and see in which case the solution lies. In all the three cases, you see that there are two integration constants. Hence, to obtain these constants, we have to find di by dt 0 and I of 0. Friends, this step is very important, for which you may have to use simple differentiation rules. While solving numerical examples, I will make these points clear. Friends, consider an RLC series circuit connected across a step input as shown in figure. The switch K is closed at t is equal to 0 and we are required to find the complete solution for I of t for t greater than or equal to 0. The system equation for t greater than or equal to 0 can be written as r into I plus L into di by dt plus 1 upon c into integration I dt is equal to v. Let it be equation 1. By substituting the values of r, L and c and v and differentiating it with respect to t, we get the standard form of the second order ODE as d squared I by dt square plus 2 di by dt plus I is equal to 0. Let it be equation 3. Substituting the values of R, L and C, we get alpha is equal to R by 2L, which we get equal to 1, and hence alpha square is equal to 1. Similarly, omega naught square is equal to 1 by LC and omega naught square also is equal to 1. Hence, we see that alpha square is equal to omega naught square. Means the system response is critically damped, whose solution is given by I of t is equal to d1t into e to the power of minus alpha t plus d2 into e to the power of minus alpha t. Let it be equation 4. Now, we have to find d1 and d2 by finding I of 0 and di by dt 0. To find I of 0, consider the circuit at t is equal to 0 minus the switch K is open and it has remained open for infinite time before closing. So, circuit elements will behave as though they are at t is equal to infinity. Hence, at t is equal to 0 minus L is short and C is open. So, I of 0 is equal to 0 and Vc 0 is equal to 0. By substituting I of 0 is equal to 0 and t is equal to 0 in the equation of it, we get d2 is equal to 0. Therefore, now by substituting d2 is equal to 0, the equation for I of t is reduced to I of t is equal to d1 into t into e to the power of minus alpha t. Let it be equation 5. To find diabetes 0, consider the system equation 2. By substituting I of 0 and Vc 0 is equal to 0, we get diabetes 0 is equal to 100. By finding di by dt, we get di by dt is equal to d1 into bracket t into minus 1 into e to the power of minus t plus e to the power of minus t into 1. Let it be equation 5.2. At t is equal to 0, we get di by dt 0 is equal to d1, so that by equating the results, we get d1 is equal to 100. Hence, by substituting d1 in the equation of I of t, we get I of t is equal to 100 into t into e to the power of minus t. Let it be equation 5.4. And friends, this is the complete solution for I of t. Note here that while finding d1, first we use the system equation and find di by dt 0. Next we use the solution for I of t obtained and find di by dt and equate both the results to get d1. This you have to note. Friends, now consider the circuit shown in figure to find I of t for t greater than or equal to 0. The switch K is closed at t is equal to 0. By writing the system equation for time t greater than or equal to 0, we get R into I plus L into di by dt plus 1 upon C into integration I dt is equal to V. Let it be equation 1. By differentiating and dividing throughout by L, we get equation 2. Using the given values of R, L and C, we get alpha is equal to 250 and alpha square is equal to 62,500. Similarly, omega naught square is equal to 10 to the power of 6. So, we see that alpha square is less than omega naught square, which means the system response is underdamped, whose solution is given by I of t is equal to b1 cos omega dt into e to the power of minus alpha t plus b2 into sin omega dt into e to the power of minus alpha t, where omega d is equal to square root of omega naught square minus alpha square, which will give us 937.5. To find B1 and B2, consider the circuit at t is equal to 0 minus. The switch K is open and it has remained open for infinite time before closing. So, circuit elements will behave as though they are at t is equal to infinity. Hence, at t is equal to 0 minus, L is short and C is open. Therefore, I of 0 is equal to 0 and Vc 0 is equal to 0. By substituting I of 0 is equal to 0 and t is equal to 0 in the equation for I of t, we get b1 is equal to 0. So, the solution for I of t is reduced to I of t is equal to b2 sin omega dt into e to the power of minus alpha t. Now, to find b2, we have to find di by dt 0. Consider the system equation 1. By substituting the values of R, L and Vc 0 and V, we get di by dt 0 is equal to 5. But by considering the equation 3.1 for I of t and differentiating it and substituting for t is equal to 0, we get di by dt 0 is equal to b2 omega d. By equating the two results, we get b2 is equal to 5 divided by omega d, which will give us 5.33 into 10 to the power of minus 3. Now, by substituting b2 and omega d and alpha in the equation 3.1, we get I of t is equal to 5.33 into 10 to the power of minus 3 into sine 937.5 t into e to the power of minus 250 t. Friends, this is the complete solution for I of t for t greater than or equal to 0. Is it not simple? Friends, let us consider another example to find I of t for t greater than or equal to 0 for the circuit shown in figure. The switch K is closed at t is equal to 0. Writing the system equation for t greater than or equal to 0, we get R into I plus L into di by dt plus 1 upon C into integration I dt is equal to V. Let it be equation 1. By substituting the values of R, L, C and V and rearranging it, we get equation 2. Using the given values of R, L and C, we get alpha is equal to 2 and alpha square is equal to 4 and omega naught square is equal to 1. So, we see that alpha square is greater than omega naught square. Hence, the system response is overdamped, whose solution is I of t is equal to a1 into e to the power of s1t plus a2 into e to the power of s2t. We know that S1 and S2 depend on the values of the circuit elements. Hence, by substituting and solving, we get S1 is equal to minus 0.2679 and S2 is equal to minus 3.732. We shall use these later. To find A1 and A2, let us find I of 0 and Vc 0. Consider the circuit shown at t is equal to 0 minus. At t is equal to 0 minus, K is open and it has remained open for infinite time before switching. So, circuit elements will behave as though they are at t is equal to infinity. Hence, at t is equal to 0 minus, L is short and C is open. Therefore, I of 0 is equal to 0 and Vc 0 is equal to 0. If we substitute I of 0 is equal to 0 at time t is equal to 0 in equation 3, we get 0 is equal to a1 plus a2 or a1 is equal to minus a2. Now, to find di by dt 0, consider equation 3. By finding di by dt and substituting t is equal to 0 in it, we get di by dt 0 is equal to a1 s1 plus a2 s2. But By considering the system equation 1.2, we see that 4 into I of 0 plus di by dt 0 plus Vc 0 is equal to 100, and we know I of 0 is equal to 0 and Vc 0 is equal to 0. So di by dt 0 we get equal to 100. Hence, equating both the results, 100 is equal to a1 s1 plus a2 s2, and we know a1 is equal to minus a2, hence we get 100 is equal to a1 into s1 minus a1 into s2, from which we get a1 is equal to 100 divided by s1 minus s2, and a1 we get equal to 28.86. Now, substituting s1, s2, a1, a2 in the system solution, we get I of t is equal to 28.86 into e to the power of minus 0.2679 t minus 28.86 into e to the power of minus 3.732 t. Friends, this is the complete solution for I of t. Friends, here is a very interesting example to find I of t for t greater than or equal to 0. Note that the switch K is opened at t is equal to 0, meaning the switch is a normally closed switch. First, let us find the initial conditions. At t is equal to 0 minus, the switch is closed as shown in figure, and it has remained closed for infinite time before switching. So, the circuit elements will behave as though they are at t is equal to infinity. Hence, at t is equal to 0 minus, L is short and C is open. Since C is open, note that no current will flow through this 5 ohm resistance. If we write the Kirchhoff's voltage equation for the closed loop, we get plus 20 minus 10 into I0 minus plus 10 is equal to 0, which will give us I of 0 is equal to 3 amperes, and hence IL0 plus also is equal to 3 amperes. To find Vc0 minus, consider the circuit at t is equal to 0 minus, is closed, no current will flow through this 5 ohm resistance. Since IL0 minus is 3 amperes flowing from B to A as shown, the voltage across 5 ohm resistance VR is equal to 15 volts with the polarity as shown in figure. Since the current through the capacitance branch is 0, Vc0 minus is equal to VAB. So, VAB can be written as minus 10 plus 15, which will give us 5 volts with plus towards B and minus towards A. Note that identification of polarity of voltage across the capacitor is very important. So, you find that Vc0 plus also is equal to 5 volts with the polarity shown. Keep this in mind. Now, to find I of t for t greater than or equal to 0, consider the circuit at t is equal to 0 plus as shown in figure. K is open. No current will flow through this 5 ohm resistance, but initial current in the inductance at t is equal to 0 plus will circulate in the loop shown. Hence, by writing the Kirchhoff's voltage equation for the loop, we get minus 10 plus L into di by dt plus 5 plus 5, 10I plus 1 by C into integration I dt is equal to 0. Let it be equation 1. By rearranging it, we get equation 1.1. You see that this equation has turned out to be an integro-differential equation. Hence, by differentiating it and dividing it throughout by L, we get equation 1.3. By substituting the values of L and C and solving it, we get d squared I by dt square plus 10 into di by dt plus 25I is equal to 0. Let it be equation 2. Using the values of R, L and C, we get alpha is equal to 5 and alpha square is equal to 25. Similarly, omega naught square we get equal to 25, so that we find that alpha square is equal to omega naught square. Hence, the system response is critically damped whose response is given by I of t is equal to d1t into e to the power of minus alpha t plus d2 into e to the power of minus alpha t. Let it be equation 3. We know that I of 0 is equal to 3 amperes at t is equal to 0. Hence, by substituting in equation of I of t, we get d2 is equal to 3. Now, to get di by dt from the circuit at t is equal to 0 plus, we get minus 10 plus L into di by dt 0 plus 30 minus 5 is equal to 0, from which we get di by dt 0 plus is equal to minus 15. Now, by taking equation 3 and finding di by dt, we get di by dt 0 plus is equal to d1 minus alpha d2, and by substituting the values, we get di by dt 0 plus is equal to d1 minus 15. Hence, by equating the right hand side of the results for di by dt 0 plus, we get d1 is equal to 0. So, by substituting the values in equation 3, we get the complete solution I of t is equal to 3 into e to the power of minus 5t. Friends, don't you find that this problem is very much interesting? Friends, I hope you have clearly understood the skill of writing the system equations and got the techniques of finding the integration constants. In this tutorial, only few representative examples are solved to emphasize the concepts learned. During the subsequent tutorials, we shall solve some more typical numerical examples. I will be happy if this tutorial has ignited some of your thoughts. If so, please forward your feedback and suggestions to my email. Thank you for watching this video.